is Hehu from Chinese Academy of Sciences, and he's currently a professor in Academy of Mathematics and System Science. Professor Xie received his bachelor degree in computational mathematics from Peking University in 2003, and PhD degree in computational mathematics from Chinese Academy of Sciences in 2008. Professor Xie's research interests include numerical methods for PDEs and integral differential equations, numerical method for large-scale eigenvalue problems, and also machine learning methods for high-dimensional PDEs. Professor Xie, welcome, and you may want to start the presentation.
Okay, yeah. Yes, thanks for the introductions. And okay, first of all, I would like to express my thanks to give me a chance to share our ideas about this neural networks and the machine learning. And also, yeah, it is my honor to show our some ideas in this seminar. Okay, and first of all, I want to express my thanks to Professor George and Professor Lulu, and also Professor. Okay, yes, okay, yes, and some other data. Yeah, but okay, it's yeah, it's okay. First, maybe time to show. Yeah, for me, it's the ideas about this tensor neural networks, and it's for the high-dimensional partial differential equations. So this work is a collaboration with Peng Zhanjing. Okay, yes, he maybe have been visited yes your group, and another students Liao Yangfei and students Yifan Wang. Okay, okay, so this my lectures will include this 6 parts. First of all, I want to introduce our concern, this high-dimensional eigenvalue problems. Okay, this is just as an examples to express our ideas, and then I will introduce this the tensor neural networks. And okay, maybe the most important properties we will concern is about the quadrature scheme for the TNN, which is high-dimensional equations. Maybe it's different from the Monte Carlo method. And then we use the TNN to solving the high-dimensional eigenvalue problems, and maybe most important examples is Schrödinger equations from quantum mechanics. Okay. Yeah, in this lectures, we are considering this types of method. The first one is the model eigenvalue problems. Actually, it's the Laplacian eigenvalue problem, and the plus maybe this functions always maybe we call this potential function. Yeah, this and okay, we will consider this maybe the dimension D is large for these ones, and then the second equations I will introduce this our TNN for solving this Schrödinger equations. Okay, this capital N denotes the numbers of electrons. So these problems, the dimension of these problems is 3 times n. So it's when we solve the number of electrons is large. So actually, this is also a high-dimensional eigenvalue problems, and and this capital H denotes this Hermitian operator from the quantum mechanics. Okay. Yeah. Okay. First of all, yeah, this is maybe well known in our groups. So in the groups, so I just want to this PINN physical informed neural networks maybe it's the most famous machine learning method for solving the partial differential equations, and also has many other applications. So yeah, in this talks we are concerned with about the numerical method for high dimensional partial differential equations. And then also they exist these three types of method. This Debye-Gladkin method and the Debye-Riese method, and also weaker adversarial networks. So maybe yeah, as in the introductions about myself is actually in my PhD period, and maybe yeah, and that after that times I spent maybe many years to do some research about the finite element method. So maybe the variational form for the PDEs is maybe is well known to me. So actually, our way is to use variational form maybe, and also this variational form Debye-Riese or maybe Gladkin, and then always we use weak forms of PDE. So to define this type of weak forms, always we need to do the high dimensional integration. So always maybe as in the Debye-Riese method, or maybe weaker adversarial networks, they both to use the Monte Carlo process to do the high dimensional integration. But as we know, this Monte Carlo always has a low accuracy maybe, and also other yeah, disadvantages maybe, and yeah, but it actually provides maybe a way to calculate the high dimensional integrations. So yeah, actually this is a standard process for the machine learning method. First, we defined the, for example, this variational form for the loss functions. And yes, actually this is also Debye-Riese method, and plus some penalty times to for the boundary condition, and this conditions is the unitary. And then based on this loss functions, we use some types of optimization method to solve to get this minimum and to get the maybe the best coefficient of the network. And actually this stands over need we do the high dimensional integration. So always they use the Monte Carlo method, and then coupled with the stochastic gradient descendant method for the optimization. So this two yeah, it can be coupled well to solve this type of method. This type of partial differential equations. Yeah. Okay. But in our work, we maybe start from another way. So first, let's forget this Monte Carlo, and let's discuss some types of ideas about the finite element method and the machine learning method. Okay, we will from this point of view, the tensor neural network, the tensor. As we know, the finite element method, the first step, we need to build the basis, yeah, for the finite element space, and then based on this basis, we can build this linear system, and then we use some types of linear solver to solve this type of equation. Then we get this finite element functions. But as we know in the machine learning method, okay, we use neural network to build this chair function set, and yeah, this is the different things. We always use some types of optimization method to solve. Yeah, this we defined this optimization problem, and then actually the total process is a nonlinear system, or maybe nonlinear problems. So this is, but yeah, because we use the optimization method, always we sometimes maybe we don't need to care how to solve this linear problem. Yeah, even in the high dimensional case. So yeah, let's start another point. For example, the decomposition of polynomial. For example, let's consider this bi-quadratic polynomial functions. So we can write it in this way. And here, so this is the coefficient matrix. And then we can do the SVD, yeah, for this matrix. And then we can write this bi-quadratic functions at this time. So this actually, this maybe we can call this SVD for the two-dimensional polynomial functions. So for this, we decouple this the first variable and the second variable. So, but yeah, okay, this maybe no applications, but let us consider this integration property. For example, let us consider this double integration for in the two dimension. So yeah, okay, the domain is a tensor type, yeah, and then we can do this separating way to compute this double integration. As in the right hand side, we only need to the one-dimensional integration. So if we generate this way to the high dimension, yeah, as okay, the matrix maybe will become some types of tensor, maybe of higher order. For example, the dimension is D and the tensor is order D. But for this case, we only need to one-dimensional integration. Yeah, this is maybe the basic ideas for our neural network. Yeah, yeah. Before we define the neural network, we can also consider this type of way. For example, we can use the one-dimensional finite element basis. For example, this is the basis, and J means the jth basis in the one dimension, and I means the dimension index. So we can yeah, we can build this maybe you can call this the chair function. Yeah, from here, so we can find this is a tensor type of way to build this the function, maybe the approximate function. So from here, so this ni denote the number of bases in the ith dimension, and this notation p yeah denotes the length of our maybe of our tensor functions. Yes, and another point of things, actually we straightforward use this tensor decomposition way to build this the chair function to do the to do the discretization. But the most another important things, we use the optimization method to solve this optimization problem. For example, we can also use the reason way to define the equivalent problems for the finite element method. Yeah, or maybe a partial differential equation. Yeah. Okay. About the length p, we always can can use the adaptive way to choose this length p. For example, we can consider the second order elliptic PD, and this time, okay, this when d for example larger than 3, we always call this is a high dimensional equation. Okay, and then phi ij is said to be the one-dimensional linear finite element method. Let us consider this degree of freedom yeah, for example, the standard finite element method, yes, from here, so this one of h is also cubic, so it's actually it's very large. And then if we use the tensor type of discretization method, okay, the DLF is maybe very small, yeah, for the d-dimensional domain. Let us use to do this, use this two terms to denote the error. For example, this is H1 known and this is L2 known. Yeah, let's check this. Maybe yeah, actually, if we use the standard finite element method to solve even 3D, yeah, three-dimensional partial differential equations, so always we need to supercomputer, yeah. But if we use a tensor type of discretization, you can use yourself as a laptop to do this computation. So for this one, this is a three-dimensional case, and this is linear finite element method. You can find this is the first convergence order for H1 node, and then the second convergence order for the L2 node. And this two pictures is for the three-dimensional and yeah, the P3 element, yeah, and you can find this for the H1 nodes the third convergence order, and this for fourth convergence order for L2 node. Actually, in the finite element theory, they are optimal convergence order. And then, yeah, let's consider this the 5-dimensional. Yeah, even okay, we can call this high dimensional, but we can also find they have optimal convergence order. Maybe, for example, this is for linear, and this is for the quadratic. Yeah, he has the second convergence order for H1 node, and the third convergence order for the L2 node. So yeah, this is maybe a tensor type of discretization, but as we know, yeah, we cannot use the adaptive refinement or maybe adaptive or moving meshing, this type of method to improve our accuracy, or maybe to compute the problems with the singularity. Yeah, this may be okay. This is a neural network has this type of property. Yeah, he can do the adaptivity, or maybe he can choose some ways to get the optimal accuracy under the constant number of or maybe fixed number of coefficients. So yeah, this is our setting for the problem. For and maybe it's we only consider this is the domain is a tensor type. Yeah, and then we build D subnetworks, and okay, this is this okay, and for each subnetwork is from R1 to RP. Okay, this is the form for the subnetworks in the ith dimension. And then we constructed the tensor neural networks as actually it uses the tensor type product way to process the rank P to construct this neural network. Actually, okay, and based on the above introductions, we can know this functions okay is easily to do the integration. So actually, I would say we use the direct tensor decomposition structure. Actually, this is our chair function, and this is the architectures of TNN. Actually, I would like to say actually from the architectures is similar to the mean on net from the Lulu and the Pengzhan, and but we are different considerations here. So we we use this type of architectures to build the approximation to the high dimensional function, and yes, and that mean not consider the approximations to the operator, and yeah. We use this architecture to solve the high dimensional equations. So yeah, this and okay, for the approximation, yeah, high dimensional functions.
Can I ask a question?
Yes. Yeah.
Do you have a specific activation function in mind? So when if the goal is to come up with a good quadrature rule,
yeah,
for example, Rayleigh equals linear, do you have those kind of assumptions built in here?
Yes. Yeah. Actually, you mean this way?
Yeah. Do you have what is there a restriction on the form of the fees? Is it like a shallow Rayleigh network, or is it any general neural network?
General network. Yeah. Maybe. Yeah. You can also use other type of neural network to, but you only need to use this tensor type way. Yes. For example, deeper network also can also can be used to construct this type of maybe architecture, and coupled or maybe combined with tensor tensor type way. Actually, for example, the subnetworks, maybe you can use free. You can also use other types of networks. Yeah.
Okay, thank you.
Yes. Okay, thank you. Okay, maybe the different things. So, for example, for any function belongs to the actual M. But yeah, we for the accuracy epsilon. So okay, we would say there exists a positive integer p, such that we can satisfy this approximation, or maybe this type of accuracy. Yeah. But yeah, how large of this line can maybe need more research, or maybe actually maybe need more conditions about the function fx. So this actually this need more research about this boundariness of the length p for the general tensors, or maybe general high dimensional functions. Yeah, this is this need further research maybe. Okay, in order to this is the same idea, but we only need to use some more complex functions, or maybe more complex TNN functions. Okay, this M denotes some types of differential term. We actually want to do M times differential to the functions by TNN, and this is index according to this the differential index. So actually, this is some types of notations to denote our function. Our function fx. So you can you can skip the details. For example, this is the number of the sets of this B and A. So they always have this this type of estimate. Yeah. And I would say this is a polynomial scale of the dimension. And then let's consider this maybe because we solve the partial differential equation. So always we need to do the differential to the TNN function. So we use this way to denote our functions for integration. So actually, this is also some types of tensor product way, and times the coefficient functions also has this type of structure. Yeah, so it's also some types of tensor product way. So for this way, okay, this is some types of index. Yeah, you can secure now. So and for this type of functions, yeah, yeah, it's also this tensor types tensor product way. So for these functions, always we need to do the high dimensional high dimensional integration. So you can only need to do the one dimensional. So actually this is a one dimensional function, and this is a one dimensional integration, and times then and then to do the summation. So actually this is our the way, or maybe this is our way to do the high dimensional integration for the TNN function. So maybe this is the application, maybe this is the important application of TNN to do the high dimensional. And yeah, in order to design the numerical scheme, for example, the numerical quadrature for the TNN function. Yeah. Okay, here, so we use the Gauss pointer, and maybe you can also use the other types of quadrature schemes to do the one-dimensional integration. So actually, this is a delector. Maybe this is a standard way to do the numerical integration. So yeah, I would to introduce this the computational complexity for the high-dimensional integration. Yeah, actually. Okay, this is a TNN for the high dimensional, for the dimension of D. So this is the estimate for the computational complexity for the numerical integration. So from here, so we can find that this is also a polynomial scale of the dimension. Here's D, and this here's D. Always, for example, for the second order elliptic problem. Actually, this m equals 1. So this actually this is a quadratic of dimension. And now we use the TNN to solve the high dimensional eigenvalue problems, because actually the eigenvalue problems is very yeah, in my opinion, it's a very good examples for machine learning, because there's no other things. For example, the right hand side 10 is also the unknown, the eigenvalue, this is the eigenfunction. Okay, the only one, yeah, other things is the potential 10. So you can also delete this 10. So there's not any other things, is only eigenvalue problems. So, but here, so we consider some types of, for example, the potential functions. Okay, this zero function is very good, and there's no other things, and but we always this harmonic oscillators from physical field. And okay, both these examples has the exact eigenvalue and the eigenfunction. So yeah, in order to define the loss functions, we consider this only consider this smallest eigenpair. Yeah, here's actually we consider the Lillet quotient for the eigenvalue for maybe for the smallest eigenvalue. So this is maybe standard ways to define the eigenvalue. So yeah, you can also define the maybe the eigenvalue which is not the smallest one. So and here we use this this way times this two times to do the deleterious boundary conditions. So yeah, we borrow these ideas from other papers. So and we just want to use to make this TNN functions to belongs to the H01 subspace space. And yeah, based on this definitions, we can define this optimization problem And then if we use numerical integrations, so we can define this loss functions for machine learning. So actually, yeah, yes, we use the PyTorch. Yeah, we use the PyTorch and the Learner. Okay, this is from, yeah, we learned this from Peng Zhan. This is the software to solve the partial differential equation, maybe to do the machine learning. Yeah, it's very good. And then we also use the Adam method. Is adapted to solve this optimization. And with this is a learning rate. Oh, okay. Let's introduce the numerical results. For example, for the actually for this dimensional cases, we use the length equals to 5. Actually, the length is very small, and we use only 2 hidden layers, and in each layer 2 hidden nodes. We use 10 nodes, and then we use this type of active function, and then learning rate we just this. And actually, okay, please note this okay, the eigenvalue, the area for the eigenvalue, okay, it is easy to compute, but to compute the errors for the eigenfunction approximation, for example, this L2 node and H1 node, actually, because the exact eigenfunction and our Tn functions can be to the high dimensional equations with high accuracy. So actually, we would like to say these two errors maybe is true error. So because we don't use the Monte Carlo method to compute the errors. Okay, this is the errors for the eigenvalue and the eigenfunction approximation in L2 node and H1 node. From here is the accuracy is better than maybe the method based on the Monte Carlo process, and this is the convergence behavior. From here, so we can find that the convergence behavior is also stable because our high dimensional integrations actually is very accurate. So it's not like it's not like the method maybe based on the Monte Carlo. So always is maybe highly oscillation. So and okay, this is this is the second example for the harmonic oscillator. Always the same settings for the network, and this is the errors result. Okay, this is the eigenvalue, eigenfunction, so has the same the similar results as the model problem, and this is a convergence behavior. Okay, it's maybe higher oscillations than the model problems. So actually, this is the oscillations. It come from the optimization process. So actually the integration is very accurate. So but the optimization process maybe need to improve maybe this maybe need to enhance for the machine learning process. And okay, I just introduce some considerations about the numerical method for the Schrödinger equation. Actually, it's almost the same as the model eigenvalue problems. The only difference seems maybe this time, this problem, this case, maybe the differential operator is more complex or maybe more complicated, and also it includes the single integration. So if you if you use a tensor type discretization with the finite element basis, maybe it is not a good choice for this type of problem, because just has actually this is a singular. Yeah, this is a singular, and also this has a singularity. So always we need to use some types of adaptive refinement method for to treat this type of singularity, and also machine learning or maybe machine learning based on the maybe neural network based machine learning can treat this type of singularity. Yeah. Okay, this is some computing techniques. For example, we use sphere coordinates, and this is the formula for the Laplacian operator. And I want to point out that maybe express our consideration about the quantum mechanics. Always actually in quantum mechanics, always we need to use maybe computer some types of operator, maybe computer the value of some types of operator. Always we need to do the high dimensional integrations for the wave function. Unfortunately, the wave functions is always high dimension. So actually, this is maybe has some use, or maybe has some applications to the quantum mechanics. Maybe, for example, the electronic structure computing. Okay, this is our way to do maybe the signal integration term. Actually, is from come from the Coulomb potential. So we use this type of associated Legendre polynomial expression for this time. From here, so we can also find that this is also a tensor type of way to express this this time. This is signal time. And okay. In order to define the loss function for the Schrödinger equations, okay, this time is also the same as the model eigenvalue problems, but these two times it denotes this penalty time to make the wave functions to satisfy the exchange anti-symmetry. Yes, because the anti-symmetry come from the Pauli exclusion principle. So we need to do the exchange operator, and then, for example, this distance. Okay, if we do the exchange operator to the wave functions, and then to do the inner product with the function itself. So and actually this should be equals to -1. So yeah, actually we do we treat this constraint conditions by the penalty way. So maybe it's also make optimization problems maybe more difficult to solve. Yeah, this is maybe this is the problems about the Schrödinger equations. So you can also maybe other ways to treat this anti-symmetry property, maybe anti-symmetry condition. Or yeah, uses the numerical integrations, so we can also define this loss function for the Schrödinger equations, and then we also use the Adam method to solve, or maybe to do the optimization process. And okay, this is almost the same. And then okay, we solve this type of this examples for the molecules and atoms. So actually, yeah, actually this examples from the physical papers, or maybe also from the papers, yeah, other people to do the machine learning method, and we find that the accuracy is better than other ways, maybe so far, yeah. And also this is the accuracy for the anti-symmetry or maybe symmetry constraint. Yeah, we can find that this also satisfies with a high accuracy. Yeah. Okay, this is maybe this electronic distribution pictures. Okay, this is for the Lee Autumn. Yeah, it includes 3 electrons. Okay, this is the one, this is the second one, and maybe this is the third one. Okay, this is the first one, the second one, the third one. Yeah, it in the second option. Okay, and okay, this is the electron discharging for the helium ion. Yeah, it's include maybe three electrons. And okay, I would express the new things is we can also use the TNN based machine learning to do the molecular structure computing. Okay, yeah, for simplicity, maybe for more electrons, maybe it is more difficult. But for the two electrons and the plus two atoms, we can also solve this type of structure problems. And this is the result. Okay. And this problem is about the electronic structure, but this is the molecular structure. Because the molecular structures include some heavy atoms, so the problem will become much more difficult to solve, and also the optimization problems also becomes very difficult. Yeah, and okay. In my lectures, I just introduced maybe a tensor neural network for solving the high-dimensional eigenvalue problems. Also, yeah, you can solve other types of partial differential equations, and also actually this is we do the numerical test for the model eigenvalue problem and the Schrödinger equation. Okay, this is maybe is an important one. And actually, different from the Monte Carlo method, we actually maybe we need a new way to solve the high-dimensional partial differential equations. Okay, and maybe there's also some other questions you need to study. And for example, the length. Yeah, for the general functions, actually we we don't know the length, the exact length, or maybe the wanted length for the tolerance. So yeah, maybe from a numerical field, for example, we can use first we compute with some length, and then we need to check this length is enough or not enough. Then we can improve this length. And but this is a numerical way, and maybe a practical implementation way. But for this way, we need to do some research about the posteriori errors made for the TNN based machine learning method. And actually, we could say there we also maybe we also need to develop the more accurate machine learning method to to couple this high dimensional or maybe more accuracy integration for the TNN. So for example, we can find that this actually this actually the accuracy is not so good for the eigenfunction. Even we had the very accurate the eigenvalue. We find, for example, here actually the oscillation maybe come from the optimization process. So for this question, actually we need to develop maybe better or maybe more accurate optimization method to solve the optimization problems included in the machine learning. So if someone introduce the TNN, you can check this two notes of papers. Actually, we will upload the new versions based on the review reports. Okay, yeah, that's all my lectures. Thank you very much. Yeah.
Thank you, Professor.
Yeah.
Do we have any question from the audience?
Yeah. I've got a question. I'm Suku here. So you compute only the ground state, right? You don't compute the higher states, higher energy states.
Yes, yes.
Because when you compute the higher energy states, you need to orthogonalize the eigenfunctions. So it's much more difficult, right?
Yeah. Yes, I think so. Maybe yes, more difficult. Yeah, as I said, maybe. Yeah, the optimization problems maybe becomes more difficult maybe, and also maybe we need to develop some maybe better optimization methods to solve this. The included included in the machine learning problems. So, and also actually I hope maybe this optimization method has maybe better accuracy. So. Yeah.
Okay, thanks.
Thank you.
Nat, you want to ask something?
Sure, yeah. I'm Nat Trask from Sandia National Labs. We looked at this similar problem for quadrature for tensor product networks. And there's a challenge with, if you use a Gauss quadrature style integration, if you have singularities, the activation functions can localize around the singularity, and you're forced to use many, many Gauss points in order to actually cluster them, you know, to get sufficient density around the singularity. So there's, I just want to share, there's a paper that my postdoc worked on that you might be interested in. I'll put a link in the chat for the lowest order. So if you have like a shallow ReLU network, you can actually work at closed form expressions for the quadrature rule. So that, you know, it's just like an analytic solution. There's no no inexact quadrature in there. So you know, I thought you might find it interesting. I'm putting it in the chat now.
Yes, yeah, I agree with you. So, yeah, maybe yes. As I understand, maybe for example, if we use this, because actually this is not a standard finite element basis. Yeah, okay. As you say, maybe for the low dimensional equations, maybe. Okay, we have the techniques to cheat the singularity. Yeah, but if you use the TNN's way and use the classical the way to, for example, the classical way to build the basis and the spaces, sometimes you can you can you can do the maybe moving your interpolator pointers, but for example to the singularity in only one dimension, but in the high dimensions, so it's not so easy to analyze how to move and to get maybe the best efficiency. So in my opinions, maybe the machine learning method has the property to do the adaptivity, or maybe actually, okay, the adaptivity notation maybe from the finite element method. So actually, for the machine learning, he will use the best way to get the accuracy. So yeah, and okay, for my understanding, maybe maybe the way of tensor also maybe will yeah, we are bring for the difficult to do the for example, to do the adaptivity of the machine learning. Maybe, yeah, as we can find this maybe for this type of more difficult problems, yeah, it's not so easy to solve this concern that maybe associated the optimization problems. Yeah, sometimes we need to do more research about the maybe optimization process.
Yeah,
we
challenge
need a
is
high.
that the neural network brings adaptivity in your shape functions, right? But it doesn't bring adaptivity in the quadrature, right? So
yeah.
you know, I think the objective, like, how do you get both of those at the same time? That seems like an open question to me. But anyway, thank you. Nice talk.
Oh yeah. Oh, okay. Thank you. Yes.
Nat, did you try to use adaptive activation function?
Yeah.
To see how? No, I'm talking to.
Oh, that's a good question. No, we didn't do that. We were using the POU nets, right? But it was just like a ReLU network under the hood for a POU.
Right.
But that'd be interesting. Yeah, the question is like
possible.
if you get more adaptivity, right? Yeah, good suggestion.
Yeah. Okay.
Any question from the audience? Sorry.
Hey, this is Adar from Brown. I have a short question. Can you go back to the eigenvalue problem definition? Right. No.
Okay, maybe this one.
Yes, exactly. So just to make it clear, the function v is fixed, or you're taking it as like you're generating a lot of them and then training an operator network to learn the solution?
Yes, we fix. Okay. Sometimes has the tensor type of structure. Yes.
Right. So if it's fixed, can you go to the next slide, please? Sorry, not this one. The one with the one with the architecture and then the losses.
Okay, loss functions. Okay, sorry. Yeah, this one. For the Schrödinger equation.
Okay, this one exactly.
Okay.
The one with the errors.
Okay. The one with the errors. Okay.
Yeah.
The definition. Okay. Yeah.
So if I understand correctly, yeah, exactly this one. These are the loss functions you minimize during the training, right?
Yes.
So you basically have a computation of the eigenvalues, and v is fixed. So
yeah,
I kind of got confused. Like if you already have like a ground truth of the eigenvalues on which you're training the network, why would you train the network if you have the eigenvalues already?
Oh, okay. Yes. Yeah. Okay. We change networks for this type of loss functions. Yeah. This is maybe okay. Yeah, we can compute this the errors. Yeah, because we use the TNN, so it can do the integration.
So
Adar is the comment. Just a comment. He's finding out the eigenvalues. The v is fixed, but he has to find out the eigenfunctions and the eigenvalues, and he's minimizing the Rayleigh quotient.
Yes.
He's minimizing the Rayleigh quotient. This is what he's minimizing. Rayleigh quotient.
Yes. And the eigenvalues is the value of the loss function, and the structure of the TNN is the eigenfunction. Yeah.
Okay, I'm not sure I completely understand, but okay, like I think so maybe you're getting this approximate eigenvalue, and then you want to find the actual eigenfunction. That's what you're aiming for.
Yes, you can do this way.
Okay. I'll just take a look at the
I
paper
understand
and-
that, yeah, it is possible, yes. For example, yeah, yes. Okay, you first compute the eigenvalue and the eigenfunction, yeah. Yeah, it is maybe, but I'm not sure it's maybe it is better because you need to do you need to solve two optimization problems maybe. Sometimes if the eigenvalue, for example, the unknown eigenvalues maybe is also not so easy to compute. Yeah, it's because it comes from the eigenfunction. So this Tn, and then okay from this, but okay, I would say this type of optimization problems you can compute the eigenvalue and the eigenfunction at the same time. So maybe it's more efficient, yeah, in my opinion. Yes. Okay.
Okay, I think I'm. Okay.
Adar, they do it at the same time. Adar, they compute at the same time. That's what.
Yeah. Yes.
I understand,
always
but what
this way.
confused, like, how is he using it in the loss if he's computing both of them?
You mean
my...
computer this? Okay.
The eigenvalue in the error, like you show, like you have lambda star and lambda, so you have some ground truth.
Yes.
You have some ground truth of the eigenvalues. So if you are computing both of them, I just don't understand how they appear in the loss.
Oh, okay. Yes. I need to I need to point out that okay, the and we want to maybe we only compute this smallest eigenvalue. So means the smallest term means okay, this linearly value erase it is the minimal way. So and then the minimal way equals the eigenvalue.
Oh, so the error, the error that shows lambda and lambda star,
yeah,
only for the smallest eigenpair.
Yeah, it is.
All
yeah,
right.
The eigenvalue is fortunately the value of this optimization problem. Yeah.
Okay, now I get it. Okay. Thank you.
Yeah,
Thank you.
It's a very good question. Yeah. Thank you. Yeah.
I want to ask Lulu because I didn't have a chance to ask him last time when the Korean group presented the tensor representation. Lulu, are you there?
Yes, I'm here.
In terms of the implement, I mean, the idea is the same as basically tensor product, but in terms of the implementation, do you know if they like you when you did the operator, the multi-input operator, or Jin when he's doing working that on the implementation, are they doing similar things? Do they see a huge speed up, like
Yeah,
like
I think
the Korean groups realized?
I think for the last group, the last meeting of the group, Korea group, what they did improvement of the speed up is they have a special way to compute the backpropagation. I'm still doing the standard backpropagation, but they have a special way, basically based on this tensor product structure. So the backpropagation will be much more efficient.
But have you measured it? That's why, because I was going to ask him, but have you measured how? Because
I didn't.
Raj was able actually to reproduce finally the results of the Korean group. So he gets for the Klein-Gordon, he gets a factor of 60 that they reported. So we now believe them. But I was wondering if you just improve the backpropagation, probably the factor is like 2, 3, right? Not more.
I'm not sure. I didn't test by myself.
Okay, all right.
Yeah,
Thanks.
so can I add to that? Lulu, the back propagation is a reverse mode only. So for computing the derivative in the PD, they are using the Jacobian vector product.
Yes.
Because it's mapping from the Rn to Rm cross n. So that's why like reverse mode will not be efficient. So only for the derivative in the PD, they are using the Jacobian vector product. So that's the only difference from the existing optimization procedure. So other than for loss, they are using the reverse mode. So,
okay, I see.
So that's it.
I mean, there's only one difference, right? In terms
yeah,
of
that is the only difference, except the input as a like suppose XYT. So there are 3 neural networks like that.
Yes,
Exactly. And each neural network has an input as a vector. So an output for the after tensor product, the output is like in the lattice, if this is
Right.
3 dimensions. So that's why you get benefit for using by using the Jacobian vector product. So
Okay, yes. Yeah, I remember. Yeah, got it.
yeah.
Now,
That's
what the speed up?
yeah, I measured it almost 60 times. So for Klein-Gordon.
Okay, 6 times. Okay.
Yeah, I think Amia is doing for the Helmholtz. So I think I'm doing it for Klein-Gordon. So.
But in the paper, what the speed up they claimed?
They close to that, 60 almost.
Okay, 6. Okay, got it. Thank you.
Yeah, sure.
Hehu, I wanted to share one pathology that we got stuck on with the same problem. When you do quadrature like this for the weak form, like deep Ritz style, like you're doing, you don't get the same convergence results. So
oh yeah, yes,
usually
yes.
for finite elements, you would get convergence in
okay.
SH1
yeah,
implies L2.
Yeah,
Yeah,
okay.
so you
because
can get, the collocation actually for pins, it works a lot. You would think that collocation is worse than Galerkin, but for these problems, like the literature goes way back to like adaptive finite elements with R refinement, but you can actually get sometimes it won't converge and it's doing exactly what it should do.
yeah.
Anyway, we lost a few months to that. so
No,
I thought
there
I'd
is
share.
a paper. Never mind the singularity. There's a paper. We had the guy from Stanford who showed that the variational form that Winan is using, even for these symmetric problems, has lower convergence, formal convergence, that the pins, because your pins, you're basically in the H2, but they're doing H1. So the convergence follows that. So there's actually, it was probably a year ago when the guy presented that, but there's a paper on that.
Exactly. If you just look at the slit problem for the Poisson, you'll see it that the activation functions run away from the internal singularity. It's kind of like a pathological thing that's easy to overlook. So anyway, hopefully that's helpful.
Dr. Xie,
Thank you very much. Yeah, okay, thanks for sharing. Yeah, this I will checking this paper. Yeah, thank you. Okay, I will.
Great. So now let's move to our second talk. Our second speaker is Xiaoli Chen from National University of Singapore. Xiaoli is currently a research fellow at the Institute for Functional Intelligent Materials. Xiaoli got her PhD degree from Huazhong University of Science and Technology in 2020, and her research interests include stochastic dynamics, machine learning, and scientific computing. She was a visiting student at Crunch Group here at Brown from 2018 to 2020. Welcome back, Xiaoli, and you may want to start your presentation. Yeah, I see your screen.
Yeah, okay. Okay, you can see my screen, right?
Yeah.
Okay, thanks a lot for joining this introduction. And before the talk, I also want to thank George for giving me a chance to enter the fields of machine learning, and also giving me a chance to give a talk at a Crunch Group today. And today, my talk is related to the machine learning method to learn closure dynamics and the application of polymer dynamics. And this is these are our collaborators in this project. Or if you have some questions or comments, you can stop me. Thank you. And the outline of the talk have 4 parts. First, I will introduce the motivation part. Then I will introduce the method, meaning how to do the model reduction and how to learn the dynamic systems. The third one, I will apply our method to the application in the polymer dynamics. Then I will give a conclusion. And as we all know a lot of papers related to the learning dynamics. Also, they give the data set, then learn the dynamic systems, then do the prediction. the data set, if the data is very, the dimension is very large, you can do the model reduction. If the dimension is not so large, you can directly learn the dynamic system. And we want to know how to analyze the learned model, and also for the prediction. And a lot of research care about the long-time prediction. And also we want to know, can we predict more related to the dynamic systems? I want to classify two classification of the method to learn the dynamic systems. For example, the I dot equal to F. Some classification is the unstructured approach, like the Cindy method. They use the basis function bi to approximate the F. The other one, like the fully connected neural network. Here, the L is the linear map and the H is the activation function. And this method is very easy to train, right? But maybe have some issues. For example, the long-time prediction, and if the method can interpretation the dynamic systems. And for the structure approach, for example, the physics informed neural network in Crunchy Grove, this is the loss of the data, and like use the equation of the loss function, because there will some physical loss in this equation. And the other one, like the Hamiltonian neural network, they also add the physical law of the conservation of the energy in the loss function. And the third one, like the quasi potential, they separate the F as two terms, the minus gradient V part plus the G part, and then the gradient V and the G is the orthogonal. And also like the orthogonal, I will introduce the orthogonal method later. And here, our observation data is the microscopic coordinates of the XT. And the dimension of the XT is capital D. Actually, D is very large here. And our observation data is the trajectories of the ST. Actually, the DSJ is the J's trajectory observation data here. And the capital N is the time snapshots. And we have capital G trajectories here. If the D is very large, we couldn't learn the dynamic system of the ST because it will be very difficult. But in a lot of problems, we didn't care about what's the evolution of the ST. Maybe we only care about some microscopic state of the interest, like this star T here. This star T is equal to the precise, the phi star ST. This is a known part. And our goal and the dimension is this star T is the D1. D1 is much smaller than the capital D. And our goal is how to model the dynamics of this star T, right? And the difficulty is that this star T, if we want to use this star T satisfies a closed dynamic system, it will be very difficult. The closed system means this star T may not satisfy this equation. So, for example, I want to give an example. What is the capital X and this star T here? For example, in the tension dynamics, the xt means the coordinates of the polymer chain. This is the polymer chain here. And for each polymer chain, there is a lot of beads connected together. And so the dimension of this polymer is very large. And we are not interested in the how the polymer is tended to this state. For each bead, it tended to this state. We interested in the intention. What's the intention? What's the evolution of the intention? Means this star T here. So this star T is the intention of the polymer. And in this paper, they give giving an initial condition. Or this is a intending. This is intending time. And after some time, the polymer will stretch to the unfolding state means to this one, because the length is fixed for the polymer, the length of it is fixed in here. And some trajectory is very fast and some trajectory is very slow, right? We want to explore the how the intention of the polymer, the evolution of the intention of the polymer here. And then the main issue is that how could we solve this? Because just now we said that this RT didn't satisfy a closed dynamic system. So we want to know how can we find a closed system to model this RT? And our solution is that find the closure coordinates. We set the closure coordinate as z hat t, and the dimension is d2. So then we combine the z star t and the z hat t together. We set a zt, and the dimension is d. And then the z can satisfy dynamic systems. The main issue is that how to find the closure coordinates z hat, and also how to construct the structural approach, because we want to do long-term prediction or analysis other information of the polymer dynamics. And the third one, how to learn the systems so that the system can be.
Xiaoli, I have a question because I'm confused now with the little d and the big D. So you had a capital, so Z of t is dimensional D, little d, but the coordinates are in capital D, and the D1 is what the D1 is small, but D2 is, I don't know how big is D2 is. We don't know these things in advance, right?
Oh, actually D2 is also very smaller than the capital D, much smaller than capital D. And this dimension is RD, this dimension is D1, this is D2.
Right.
And our observation data X is equal to R capital D. And the small d is much smaller than the capital D here.
Because it's macroscopic, so you integrate over many, right? That's what you're saying.
Yeah.
Okay, thank you.
Okay. So after we solve these issues, we want to do the prediction and analysis and also the interpretation of the learned coordinates or the systems. Here, first I want to introduce how can we find the closure coordinates. Here we use a PCA ResNet to find the closure coordinates because our observation data is X, right? We set ZT, actually this is the model reduction psi hat, and we set the PCA X minus encoder neural network. So the Z hat dimension is D2. And then for the reconstruction, after we got the Z hat, we need a reconstruction to the high dimension. We set it as X tilde. We use a psi function. It's defined as the PCA transpose plus a decoder neural network. Then the reconstruction loss is the observation data X minus the S tilde here. So actually the PCA is a known part, right? We only need to train the encoder and the decoder part, but we didn't. Okay, is it clear here? And then after we got the Z hat, actually we just write the formula of the Z hat T, right? That means we have got the ZT. Then how could we model the ZT? Because in a lot of systems there is a lot of stochastics, so we still use a stochastic dynamic system to describe the ZT. We use this formula. Here the F is the drift term, and the sigma is the diffusion mass term, and the B is the Brownian motion term. And then the next problem is how to construct the structure model, right? And the structure model, and I want to introduce the Osaka principle. Is a general model for near equilibrium dynamics. It looks like is this equation. Here the M is symmetric positive semi-defined matrix. It means the disruptive force, and V is a generalized potential term. But this, because a lot of polymer dynamics, or this model can describe a lot of models like the polymer dynamics. So we generalize this model as a stochastic version. We call it a generalized stochastic orthogonal principle. It means our drift term F is this one, and we added just to know the M is just a constant matrix. Here we use the equation, and the M is still the symmetric function, and W is an anti-symmetric function, and the V is still the potential, and we add the noise here. Actually, if the noise is very small, the energy V is non-increasing. And for the orthogonal, in this paper, they didn't do the stochastic version. They just consider a deterministic of this model. Okay. Then I want to give an example why the stochastic generalized orthogonal polymer is useful. For example, for the stochastic depth Langevin equation here, okay, and if we set the S dot equal to V, then this equation can write in this form. This form can write in our stochastic generalized stochastic orthogonal form, and X, M, W, and also sigma and B is equal to this, and this is the potential V. So the next question is, how could we learn the stochastic model, right? Because we contrast the stochastic model as a stochastic, the generalized stochastic orthogonal form. Then I want to introduce how could we learn the stochastic model. And we still let the drift term the F here. We use the Ola-Maruyama scheme to describe the SDE, and then we use the maximal likelihood estimation to learn the F and sigma. Actually, the F sigma means the F. It means we will construct a neural network for the M, W, and also for the V. But I didn't write the detail here. So we have constructed a loss function for the high dimension and also the low dimension. The high dimension means use this one, and the low dimension we use a maximal likelihood this one. Then we sum them together, and add a parameter lambda 1 here. The lambda 1 is a parameter to balance the two loss. Okay. Then maybe we can see the structure of the neural network. This is a high dimension observation data, and this is a known part because we are interested in the microscopic coordinate, this data here. This is known part, and this one is our learned part, the closure coordinates part. This is the ResNet, and then we got the reduced coordinates here. And for the MW, just know I didn't write the details of the MW and V. You can see the neural network here. We have a neural network to approximate the M and W, because M is symmetric and W is anti-symmetric. And also have a neural network for the potential V. Then we combine the MW-V together to get the drift term. And the third neural network to approximate the sigma, the diffusion term. Then we can use the maximal likelihood to get this loss function. And for the Z, we contrast to the high dimension to get the S tilde. Then we got the recontraction of the loss, the recontraction loss. Then we train the loss together to get this part, and also for the F and sigma. If we train well, we can get the model reduction part and the recontraction part, and also we know the low dimension dynamic systems. Okay, then I will introduce our application in the polymer dynamics. The polymer dynamics, you can see this figure for initial polymer dynamics. They can the unfolding time is very different, right? And you can see for example, for this shape, for the dumbbell state, this is dumbbell state of a polymer. You can see the dumbbell state, the unfolding time is very fast. And for the blue one is the folded state. This is a folded state. The unfolding, the polymer unfolded very slow. So we want to know how can we get an accurate dynamic model for the intention of this dark here. This dark here is the intention of the polymer, means the length, the length of the polymer. And the second one, what are sufficient descriptors that drive the dynamic systems? It means just now we use the z hat, right? We want to know, is there any physical meaning of the z hat t? And the third one, just now we use the orthogonal. We have the potential or the energy landscape there. So we want to know what can we learn from the dynamic landscape. Can we interact with it, or what the potential can give us more information of the unfolding dynamics of the polymer. Okay, then this is our data. We produce the data by the microscopic simulation of the beads. The beads means the polymer have a lot of beads here connected together. Beads and rod. Rod means for each bead there is a rod connecting them together. And the flow is in the elongational flow. This is the flow of the polymer. Our data set, we have 610 training trajectories. And the test trajectory is 110. The dimension is D. D is equal to 3 times, so D is 900 dimensions. This 3 means because we have 300 beads, and this 3 means for each bead they have XYZ coordinates. So the dimension is 900. And then we applied the stochastic orthogonal with the small d equal to 2. Small d equal to 3. So it means this star actually later we will set this star as z1, and the z hat is our learned coordinate. We set as z2 and z3. Okay, and you can see, oh, I forgot to say, if we only have the z1, we want to know. Just now we said z1 couldn't satisfy the closed dynamic system. We can see here, because for a fixed length of the polymer, it have different shapes, right? This shape, this shape, this shape. So it couldn't have the same behavior of these 3 polymers. So this is why this starch couldn't satisfy a closed system. We need to find the z hat for the polymer dynamics. And the other one, I didn't plot the figure here. You can see, actually for a fixed initial condition, the polymer also have different behaviors. I didn't plot. For example, maybe for another polymer, from this one, making like this one or this one, for a long time they will arrive at the unfolding state. And also you can see for the three initial polymers, you can see this polymer after the same time step, it was still in the folded state. But for this polymer, it have unfolding very fast. It have arrived at the unfolding time. So we want to know if our method can capture the slow and fast trajectories. Okay, so the next one, we give 3 initial, our unseen initial polymers. we predict, because just now we said we only care about the intensity, this star in our polymer dynamics is the Z1 here. For giving us a initial condition of the polymer, because there is a stochastic here, so we plot the for this figure we plot 300 trajectories. So and the black one means the true trajectories, the true intensity of the polymer, and the red one is our predicted results. We can see for this one, the polymer will unfolding very fast to the unfolded very fast, stretched very fast to the unfolding state. And for this one, that has some very fast trajectories, and also the slow one. We can see the red one can capture the fast and the slow one. And also for this one, almost all the trajectories tended very slow. Our method also can capture this, right? Then we compare the statistics of the statistic information of the polymer of the Z1. For example, the mean, we compare the mean and the standard deviation. I think we can capture very good results. And also we compare the probability density function of the unfolding time. The unfolding time means, I didn't write in here. The unfolding time means giving an initial polymer, and we want to know when the polymer arrived at the unfolding state. Then here we have 500 trajectories. So we have 500 unfolding time. We can plot the PDF, right? So we can see our method also can capture the unfolding times here. So from this figure, we can see we can capture the slow and fast trajectories. The next one, we want to know what is the physical meaning of our learned coordinates, and also why the slow and why the trajectory are slow, why the trajectory are fast. And for the physical meaning of our learned Z2, Z3, how could we do? We're giving a unique. This is we're giving a polymer dynamics of the black one. Then we add the perturbation of these two. If we add this perturbation for this one I equal to 2, it means we change the Z2 here. We change the Z2 here. For example, for the black one, we can see the Z2 is equal to 0.323. And for the green one, the Z2 becomes larger. We can see the figure, the end-to-end distance changes, right? This one, and this is the black one, and the blue one is much smaller. We can say, oh, maybe the Z2 is related to the end-to-end distance. So we plot the figure, the Z2 and the end-to-end distance. Sorry, the R is the Rn is the nth base of the position, and the R1 is the first base of the position, and X is in the S direction. And so we found the Z2 have a positive relationship with the end-to-end distance. And then in the same way, we plot these three. We found that it has some physical meaning of the foldedness of the polymer, because in our we can see in our elongational flow, if the polymer like this one and another one if looks like this one, we said this one is folded, much folded than this one, because this polymer we are unfolding very slow, because the flow maybe the first will go to the folded state than the others. And for this one, we are folded very fast, unfolding very fast. So we use this one to describe the foldedness. Actually, we use this formula to describe the foldedness of the of the polymer. Then we compute these three and the 4D-ness. We still have some positive relationships. And after we learned the 4D-ness of the physical meaning of the Z2 and Z3, we want to know what the Z2 and Z3 can tell us. And for example, in the classical method, they divide the shape of the polymer. They maybe just see, oh, what's it? Oh, this is a dumbbell, and this is half dumbbell, or this is a 4D state of the polymer. And if we use our method, we found our unfolding time can tell. Oh, sorry, not unfolding time. Just know in this figure, in the below, this figure, we can say, oh, the unfolding time, the dumbbell state unfolding time is very fast, and this one is 4D is very slow, right? But in our method, we can our Z2, Z3 can classify the different shape of the polymer. For the circle one, this is the dumbbell state, and for the triangle one, this is the 4D state. We can see the Z2, Z3 can separate very good, right? So the Z2, Z3 can help us to classify the shape of the polymer. And then I want to say to plot the energy landscape, the V energy landscape V, and because the dimension is three dimension, and if we plot the 3 dimension, it's very difficult to see. So we project the energy landscape in Z1, Z2, Z1, Z3, and Z2, Z3. We just use the minimization to project them. And then we found there are 4 critical points in the potential landscape. For example, these two points. These 2 points is a stable point of the landscape, and also there are 2 saddle points. Maybe this figure is not easy to see. We can see this figure. There is 2 saddle points here, and then we can compute because we have got the V, right? We use a neural network to approximate V. We can compute where we can compute the coordinates of these 3 points. Then we can, because this is the low dimension, then we recontract to the high dimension. We found, oh, these 2 stable points means the unfolding state of the polymer. Because these 2, we use the recontraction percent to get the high dimension coordinates. And these 2 saddle points means the 4D state of the polymer, right? And also we plot 2 trajectories. Actually, these 2 trajectories, the red one is unfolding very fast because for each point we have the same time snapshot. We can see this one will go to very fast, and for this one, a lot of points here near the saddle points. So we plot a video here. Sorry, I just make the wrong color here. The blue one is the yellow one in the video here, and okay. So here the yellow one and the red one means the high dimension coordinates of the polymer, and the black one means our learned coordinates, the low dimension coordinates. We can see now this black point is near the saddle point, and the polymer is in the 4D state. It's stuck in this point, right? So we can say, oh, it can tell me why the polymer stretch very slow or fast. Because if the polymer stretches in the saddle points, it will stretch very slow. And if the polymer is escape from this saddle point, it will extend it very fast. Okay. Then, so we have explained why the trajectory are slow or fast. From the microscopic view, the 4D state because the polymer is in the folded state, so this is slow trajectories. And from the macroscopic view, because the polymer arrive near the set points. Then we wonder how could this can tell us more information. We want to use the set point to do the control, because in the polymer dynamics, they want to add some control such that the polymer can extend it slow or control the polymer extend it faster. And we take the, how could we do? We take the Taylor extension of the V near the set point. Then the delta V means the VZ minus the VZ star. Oh, sorry, this saddle. And we use the Taylor extension. We got this result. Actually, the delta Z means the Z minus Z star. And we can see this equation tells us if we want to escape, because if Z star is equal to Z is equal to this star, then there's 0, right? But we want to escape from the set point. That means if you want to escape from the set point faster, we need, let me plot, because just now we can see the potential here. For the Z2 direction, this is a stable point of the Z2 direction, right? And this is unstable direction for the Z3. So if we want to escape from the set point, it means we want to make the delta V smaller. Make the delta V smaller means you can easily see here. We want to make this term larger. Also means we want to make the delta Z2. We want to increase the end-to-end distance and also decrease the Z3 here. And how could we do the control? We start this several steps. We start with a folded state, and the polymer trapped near the set point. And we have to the first protocol, the control protocol 1 attempts to speed up the unfolding, and the control protocol 2 aims to slow down the unfolding. How could we do? And we do like this. If the polymer, maybe the polymer is in the other point, right? If the polymer arrived near the set point, this is the set point. If arrive here, we turn, because of our flow is the elongational flow, we turn off the flow. After we turn off the flow, it only has the Brownian motion here. Then if the polymer arrived at the unstable manifold, actually this direction is computed. So the Hessian matrix of this Taylor extension, that means equal to gradient V minus Z minus Z star, and also, sorry, Z star transpose, and the Hessian Z plus Z minus Z. We compute the eigenvector. We can compute the eigenvector of the Hessian matrix to get the direction. Then if the polymer arrives near the unstable manifold, we can see, oh, the green one is the true trajectories, the true unfolding trajectories. And if we do this, we found a lot of trajectories unfolding very fast. And in the same way, if the polymer arrives near the unstable manifold, then it means to the stable point, maybe the polymer will arrive near the set point, then left. So the unfolding time will much smaller, right? And okay, this is the summary. We give a talk about the stochastic orthogonality method. Our stochastic orthogonality method can contain accurate and interpretable model of the polymer dynamics. First, we do the prediction. the slow and fast trajectory can be learned well here. And also we give some physical meaning of the reduced coordinates. The Z1 means the polymer intention. The Z2 is the end-to-end distance. And the Z3 is the coordinates of the polymer. And also we have the potential landscape analysis. We can analyze why the trajectory is slow or fast. And also we do the control, how to control the trajectory slow or fast. And also our ongoing work is application to the experimental data. Okay, I stopped very early. It's all, thank you.
Yeah, thank you, Xiaoli. Do we have questions for our speaker? Comments?
Hi, I have a question.
Mm-hmm.
Hi, I'm Vivek and I'm a PhD student working with Professor Kanidakis. So can you go to slide 17?
70. Here, right?
Yes. So here you are trying to learn the trajectories of several cases. So you said you have around 500 trajectories. Black represents true and red represents the predicted trajectories.
Sorry. Yeah.
Yes. So there are close to 500 trajectories, as you mentioned before, and they are going from time step 0 to, let us say, time step 10,000. So my question is, how much history did you have as input to the model, and how much did you forecast?
For how many forecasts? Actually, here we just give the initial condition. For example, we give me an initial polymer, right?
Yeah.
Then we can got the if we have this polymer, we can compute the Z1. Sorry. Oh. We can compute the Z1, Z2, Z3, right?
Yeah.
Then we use the stochastic orthogonal to predict. We can predict use our SDE. Okay, we use the SDE to predict the Z1, Z2, Z3.
Yep.
Because we only treated in the Z1, so we plot the Z1 trajectory here. And because of the stochastic for each, the black, actually the black one means the high dimension. We have a lot of high dimension trajectories. We can compute the intention. This is the black one. And the red one, we use the low dimension dynamics to predict the red one.
Okay. Okay. So okay. Yep. So just from the initial condition, you are going all the way till 10,000 step. For in this case, the Z1 component. Yep. Yep. Thank you. Yep.
Okay.
I think Xiaoli, I think what Vivek is so you're using the SDE in your predictions. During inference, you're using the SDE, but I think maybe you can explain how you're using the training data, because you had you separated the trajectories into I forgot how many you have, like 500 or 600 and 300, right?
Yeah.
So how do you, in what way do you use the training data, or is it just like we do in pins, and basically then you interpolate these other trajectories together with the equation?
Yeah. If we have this is the training trajectory. Actually, the training trajectory means a lot of trajectory, like the polymer dynamics intending, right? We have 600 and trajectories, and then we use our method here. Here, maybe here. You can. This is our observation data. We can train. We use the training data to got the neural network. Then we can get the reduced coordinates, right? Yeah, and also we can, if we got the coordinates, that means, and also we can got the low dimension SDE. We use this SDE to generate our test trajectory. Just know we showed.
Yes, sure. Yeah.
So Xiaoli, you're learning the SDE. You're learning the various terms in the SDE, right?
Yeah.
From the trajectory, yeah.
Yeah, we learned the SDE use a maximal likelihood method here. We use this loop to learn the SDE, meaning the drift term and the diffusion term.
But I think so that the training is over 10,000. If you want to go to 20,000
Yes.
steps, I think that's what Vivek wanted to ask. If you want to go 20,000, you don't do that, right? You just stay within the same domain.
Yeah.
Because one of the you can have an outlier, and I saw sometimes you miss the heavy tail in one of the cases for the Z2. If you look at the right there, the Z1, you miss the tail to the right at long time.
You
so
mean this one?
Yeah. So you always stay with this. In other words, if you have something really slow,
you
miss the dynamics.
Actually, you mean this here, right?
Yeah, for example.
Actually, because of the stochastics here, I think if our learned model has some, because you can also see here, there is also the black one, also it tended very slow. But our learned model found the more slow trajectories here, right?
Right, but it's not right. There's not much.
Yeah.
So we don't know if it's right or not. So, but the point is that if you have a very slow, you see here, for example, that will fall for a long time. So why don't you run for a longer time? Because you cannot, right?
You mean for
20,000 time steps.
Yeah. Actually, before our training data is only from time, the end time is here. Yeah, maybe I can try running for longer time. But when we do the control, we run the time for the longer time to see if the slow and fast. Yeah, this is a good suggestion. I think I can run for longer time for this one, right?
Yeah.
Okay. Yeah. I think this is a good point here. Yeah.
Thank you.
Oh, thanks a lot.
Xiaoli, I have another question.
Uh-huh.
So I didn't see, because I know this system of paper of Stephen Chu. I didn't see any. We used the DPD a long time ago to do this, but I didn't see any memory effect. So this all this DNA or all the polymers will have a memory at the macroscopic level. How do you bring that in the model? If you look at your equation, it has the conservative force, has the dissipative force, but where's the memory term? Where's the memory term? Can we see?
Yeah, actually here, we didn't for this one, right? Actually,
no. If you go, Xiaoli, if you go before, if you go just above, with the equation that has the gamma. The friction. There's an equation. No. There's an equation that has the friction term. There's like go further down, please.
Down, not this one.
Down, a little down. There's equation 7.
Okay.
Equation 7. 7.
This one.
7. Yeah. For example, here, right? I know this is a laundry, but gamma. If you write it in this form, for example, you assume that you have no. The last one is the random term. The first one is the conservative term, and this is the term that is the memory actually. But here you don't have any memory. Gamma is actually the integral of the covariance kernel, and that you assume that you have separation of scales, and therefore memory is not important, and you bring this out. That's why you get a constant. But in general, in the system, if you look at the Morris-Brunswick formulation, that is actually an integral go from time 0 to time t. So in your system, if you look at the Onsager non-equilibrium model, does it have that memory term? I don't see it.
Yeah, actually, I got our high dimension trajectory also generates a very high dimension stochastic dynamic systems. I didn't see some memory in the high dimension. So when we do the model reduction, we didn't add the memory here. And because, for example, if we consider the in this flow, okay, because the high dimension data is in this, maybe we see this figure. In this flow, if we have this flow and we're giving, we're giving a polymer, I don't think there is memory here.
No, because you make it very elastic, for example. I don't know, but if you make it, I mean, the viscoelasticity should come through a term. I don't see it, how you avoid that, because you're looking at the macroscopic quantity.
Yeah.
So somehow it has to come in, either through the closure or through an explicit term, or I don't know if Zhenjian is listening, but we're trying to do something similar with another approach, and you need to take into account the memory.
I know some, I'm not familiar with the DPD. I know there is some memories in that dynamic systems. I will check. I remember I checked my microscopic dynamics didn't have the memory here. I will check it. Okay.
But my sort of question is, can we look at the Onsager model again, the non-equilibrium model? Because I don't think that includes the way the M term. The M term is okay. The M term, okay. So you have the middle term. The M term is the conservative form, right? No, the dissipative. Sorry, the dissipative.
Yeah.
No, which was the conservative form? Which was the conservative part?
The M term.
That's the conservative.
Yeah, actually, our method is just a pure data driven. We don't know how to contrast the dynamic system of Z. We tried to use a generalized stochastic oscillator. We found it works so well for the prediction. Yeah.
I'm confused with this term. So the M is a dissipative term. Because this has to agree with Morris-Brunswick, which is exact. No.
I know. I will check the.
Right. Okay. No, that's fine. So actually, M is the I think M is the friction term. Yeah, that's you call it dissipative. Yeah, that's the friction term. So the middle term is actually the conservative. The last one is the random fluctuations, and then minus MZ. That's the that's the. And that has memory, but you don't have memory here unless you write it in a form that do you have an expression for M of Z of T? You have an expression for that term somewhere? You have an equation for that?
I didn't write that equation here, but I can check it later and send to you. Okay.
Okay.
I only compute the equation for the V.
Okay.
Yeah. You mean check the indentation for this term.
No,
right?
the first term actually. The first term is
this term, right?
yeah, the conservative form will not have the conservative term does have it. That term has it because that will be like the integral from 0 to t of the covariance kernel times v of the fluctuations times is basically the times v. Yeah, so that's so it's or v dot. So if it's that is basically your minus gamma x dot that you had before.
You mean
in the Langevin equation? Yeah.
Example.
Yeah.
Sorry. The example here, right?
Yeah, that's why you can see it from. Yeah, exactly. Yeah, and your first term is your middle term.
Okay.
Yeah.
Yeah.
Anyway, these are interesting results that you actually have access to Z1, Z2, Z3, which are physical quantities, and therefore you can interpret like so. So your conclusion about interpretability is really interesting.
Yeah. Maybe in the future we will consider the memory in our system. I think this is good. Okay.
Good to see you, Xiaoli.
Me too. Good to see you. And
although we didn't see you, but good to hear you.
Okay, thank you. I'm very glad to see the Crunchy members again, like Zhongren and Lulu, and also other people here. Yeah.
Cool. Yeah. Do we have any more questions from the audience? All right. Now we're closing this week's Cron seminar. For our speakers, good night, and everyone has good evening and afternoon and weekend. See you next week.
Okay. Bye.
Bye.